In this video, we're going to look at how we actually use Gauss's law to think about the electric field. Specifically, the concepts behind Gauss's law, and then we're going to look at some situations that we already know the answers to, in many cases, to try and figure out what's happening. So we know that Gauss's law says that the net flux through a Gaussian surface, which is this enclosed surface, is equal to Q enclosed over epsilon naught. This is one of Maxwell's four equations, which are the equations that describe electricity and magnetism. And it tells us a way to make the electric field and how to calculate its magnitude. This doesn't work for many situations, but it works for a lot of really interesting situations, specifically those that are highly symmetric, and we'll see what we mean there. We can do point charges. We also have another method for that, but this one works just fine for point charges as well. And that's where we're going to start because those are the simplest to think about. Infinite charged lines and cylinders, which is like a wire charged up. It's a good way of thinking about it. Capacitors also fall into this category. More on those later. And then infinite planes of charge where the electric field is constant. And so we've got these sort of different relationships, 1 over r squared, 1 over r, and then a constant or uniform field. And this is an important idea that although it is not a reality to have an infinite plane or line of charge, that's not something we actually encounter. What we can do is we can get really close to a line or plane of charge, and then the infinite size is a good model. So we're going to do 3 things. We got to figure out what the electric field looks like just direction-wise, and this is using what we understand about how the electric field behaves. Then we're going to create a Gaussian surface, and this is the new piece. This is the special physics thinking for Gauss's law. You want to make sure the area vector is either parallel or perpendicular. Perpendicular would mean, right, the dot product would be 0. Parallel would mean the dot product would just be the magnitudes of the electric field and area multiplied together. And we want that for every single part of the Gaussian surface. Sometimes part of it will be parallel and part of it will be perpendicular. More on that. And the point we're trying to figure out, the place in space where we want to know the electric field, needs to be on this Gaussian surface. It can't just be some other arbitrary place. Then we'll actually use this equation up at the top. So we can do this for a point charge, something we've done before. And if you're following along, this is the Coulomb's law part. We're going to go ahead and look at page 20 in your packet in just a moment. But if we use Coulomb's law, the electric field is kq over r squared. We're 50 centimeters away from the center of the charge. We just plug everything in and we get the electric field magnitude. And we know it is away from the positive charge because that's what a positive test charge would feel at that point. Now, if we're to use Gauss's law, we need to follow our procedure, which is first to sketch and visualize the electric field radially outward. We draw a Gaussian surface. And now, because this is in a two-dimensional plane, the drawing space, right, the screen, I have just drawn a circle representing the whole sphere around it. And that sphere or that circle goes through the point that I care about, that is 50 centimeters from the center, right? And what we have done is we've picked a Gaussian surface where for a sphere, the area vector is always pointing radially outward, which means it is always parallel to the electric field lines. And not anti-parallel, just parallel. Point P is on the Gaussian surface. All of our criteria are done. Now we can state and solve. So the electric field dotted with dA and then integrated all over the place is going to look like this. And so a brief word on what I did there. Well, I know that the electric field is constant everywhere on this surface. And I know that the area of the sphere, right, is any area vector for any bit of electric field. These will be in the same direction. So the dot product will have the cosine of 0. And then the surface integral is really only adding up what is the whole surface area of the sphere. And that we go to our formula that we know, 4 pi r squared is the surface area of a sphere. And so what we've done here is what we're always going to do. We are going to set up this surface integral, and then we are going to set up our Gaussian surface in such a way that it becomes a simple integral, and we're not actually computing a surface or a closed integral so much as using that idea to tell us something we might already know. So if we rearrange that, you get Q enclosed over epsilon naught 4 pi r squared, plug in your values, and you get the exact same answer. Right? The direction we already determined, we did that in an earlier step. That's kind of the difference for us in using Coulomb's law versus Gauss's law. In Gauss's law, we're always thinking about the direction of the field in the kind of first step. So if you turn to page 20, we are going to look at some situations where Gauss's law is an appropriate method for doing this. You can follow right along. This is the thing that you should, once you're done, take a picture of and upload it as evidence that you've gone through this. And again, we're going to follow our 3 steps. So here is our first one. Example 7, as it's listed, a point charge. What is the electric field a certain distance r from a point charge? Well, if we draw the point charge and we draw the r distance, right, the next step is to draw the electric field. Now, I have called this positive, right, as it says, positive Q. If you didn't know whether the charge was positive or negative, you could always just draw it as a positive, but make yourself a note saying, I'm not sure. There's our Gaussian surface, right, which goes through the point we care about, a certain radius r away. We now state Gauss's law, and just as we did before, we said the electric field, which is a constant everywhere on that surface, and the integral, the closed integral over a sphere of the surface area is 4 pi r squared. The directions of the both 2 vectors are in the same direction, so we get cosine of 0. We have Q enclosed over epsilon naught. Q enclosed in this case is our positive Q, and we end up with our E for a point charge is Q enclosed over epsilon naught times 4 pi r squared, which hopefully looks familiar because 4 pi epsilon naught is 1 over k. So we end up with kq over r squared. So we get the exact same result symbolically as we would for Coulomb's law. And that's good. We want to make sure that we get the same result. We did one with numbers. We've now done one symbolically. Now, the next example is an infinite line of charge. So we've talked about lines of charge and how we think of them as having a linear charge density of lambda. In this case, we're interested in a point some distance from this line. Now, this is interesting because it seems like this is a 2-dimensional problem. But if you imagine a line of charge, basically a wire that's charged up, the number of points or the collection of points that are a certain distance r from that line of charge actually form a different shape. They form a cylinder, right? And so this is looking at it from the end. If you could let the wire kind of start at your face and run that way. And so if we sketch the electric field from the perspective of the side, it's going either up or down. From the end perspective, it's going radially outward, right? This isn't spherical symmetry. This is cylindrical symmetry. And so we can draw our Gaussian surface, and I'll move myself out of the way a little bit. And from the perspective of the end view, it looks like a circle. But from the perspective of the side, we're basically going to wrap it around in a cylinder, like a can, right? If you imagine taking a can of soup or something, or beans or whatever you put in cans, lots of things, and you just sort of poke a hole one at each end and slide the wire through, then you can imagine the shape of it. So a few things we need to know about a cylinder. It's not just the radius of the cylinder, although that is important, but we also need to know how long the cylinder is. Not because the cylinder couldn't be any length, but because we can't make it infinite length. That doesn't actually work. Then we would have an infinite area. So we're going to pick just some finite amount that looks like this. Notice again, the point P is on the Gaussian surface. The area of this thing, right, the area of the part that is wrapping around is actually 2 pi r, the circumference of the circle, times L, right? If you were to cut that can and unfold it, right, basically unfold a roll, you would have a rectangle. There's also the area of the 2 ends, but we'll get to that in a moment. We can figure out the electric field at point P by using the electric field dot dA is equal to Q enclosed over epsilon naught. In this case, Q enclosed is the length of the Gaussian surface multiplied by lambda. That's how much charge is in there, because lambda is charge per unit length. And the area of that lateral surface area, basically the out the edge, the side of the can, is 2 pi r times L times the electric field. We don't need to include the end caps. I'm saying we don't. But why not? Well, if we think about those two, right, if you cancel everything out, we get this relationship, lambda over 2 pi r epsilon naught. But again, why don't I need to worry about the end caps? Well, what does the area vector look like for the two end caps, the two circles? Well, they're left and right. And left and right are perpendicular to the electric field. So if I were to do the calculation of the surface integral of E dot dA for those two end caps, I would get 0. So essentially what I'm doing is taking every surface and kind of making a judgment call. Is this one going to give me flux or not? And in this case, I set up my Gaussian surface so that only the lateral surface area has flux through it, and the other two surfaces do not. So there's our results, 2k lambda over r. So for any long line of charge, 1 over r is the relationship for your electric field. So what happens then, if we look at a few examples, if you double the radius, what happens to the area and to the electric field? Well, if you go to some new p prime, right, we have to draw a new Gaussian surface, which is bigger, right? But if the radius doubles, the area doubles, and the electric field strength goes down by half. So we have our cylindrical spreading 1 over r relationship for the electric field. Last example of this type, and for this video, is example 9, an infinite plane of charge. So when you've got an infinite plane of charge, I've drawn a finite one here, but we'll consider it goes on forever, with a surface charge density of sigma, some number of coulombs per square meter. We want to know what the electric field is a certain distance r from that plane. Now, we've already learned that this should actually be a uniform field, a constant electric field, and it shouldn't depend on distance, but we want to show that using this method as well. So we start by visualizing, and then we're going to draw the Gaussian surface. So here's my Gaussian surface, right? I've done a cylinder because a cylinder is a simple shape. It only has 3 sides. I could also do a cube or a rectangular solid, but then I'd have to make the argument multiple times. And so this is easier. The area, there's 3 areas I'm sort of interested in here. There's the area of the 2 end caps, which have the area vectors up and down. And then I have the area sort of punched out or enclosed really of the infinite charge plane. So the area of each Gaussian cylinder, of the Gaussian cylinder, is the area of each end cap. That's what matters. Q enclosed over epsilon naught. So if we think about the 2 ends, right, and the electric field is up and down, each of them gives you an electric field times the area, right, pointing straight up, whatever that electric field is. And you get twice that because you have both of the effects of it. And Q enclosed is going to be sigma times the area of that circle. If you rearrange that, you can cancel out the A, and you end up with the electric field is equal to sigma over 2 epsilon naught, which is a constant, which is also the result we got from integrating Coulomb's law. That was just a more complicated setup. It helps that we already know that, right, the electric field is pointing away from the plane of charge, so we can get that as our result. Same result as example 5. All right, so there's a couple of other things to think about here. What if we have, instead of a point charge, we have a sphere of charge? Well, if we have a conducting sphere, all the charge is on the outside, so the charge density in the middle is 0. And if you have an insulator, you could spread the charge out and maybe give it a constant charge density. In each case, right, just outside the field, if they both have the same amount of charge, right, we get the same result for the amount of electric field, because all we care about for Gauss's law is charge enclosed, and then we care about the area of the Gaussian surface. And if these are 2 identical radii or radius spheres, and with the same amount of charge, you've enclosed the same amount of charge and you're the same distance from the center because you have the same radius of your Gaussian surface. Now, once you go inside, things change, right? The conducting sphere will be Shell theorem stuff, and the insulating sphere will be the idea of tunneling inside the Earth, where you get less and less charge enclosed, meaning you get a weaker and weaker electric field until you get to 0 at the middle. Right. So that's kind of the layout here. The next piece is looking at a bunch of different examples of this. And you may need to, this is in red, figure out how much charge is enclosed. Sometimes you have to add up all the dq. This is really like, you're just adding up all the mass that's inside of, the Earth or something like that. Same basic idea. And we'll talk about this when we get together in class.